Greetings. One may wonder why I am giving this talk, because it is a conference on gravitational waves, and I am giving a talk on probing neutron star core matter using observations from electromagnetic wavelengths. There can be several reasons. Number one, gravitational wave window has become available only recently, but for decades, people have used electromagnetic observations to address this particular scientific problem. So this talk is necessary to put this science in a bigger context. Second, in some cases, gravitational wave observations and electromagnetic observations can help each other to address this particular problem. And third, here I am considering the probing of superdense degenerate core matter of a stable neutron star. But for merger, it is a dynamic system, and then if one considers post-merger to constrain equation of state model, that equation of state may be somewhat different from the equation of state I am considering here, because there it is hot and might not be degenerate. Therefore, in this short talk, I will very briefly and very quickly describe some of the X-ray observational features which can be used as tools to probe neutron star core matter and to constrain the equation of state models, which can be done if one can measure the mass, radius, and spin frequency, or any three independent structural parameters of the same neutron star. And for this, I am choosing a particular type of neutron star systems, the neutron star low mass X-ray binaries, in which a neutron star here at the center is accreting mass from a binary companion, which is a low mass star, and this matter is flowing towards the neutron star via a disk called accretion disk, and the inner part of the disk is very hot. The temperature is of the order of million degree Kelvin, and therefore such sources primarily emit X-rays. I choose this kind of system because such a system can provide many complementary methods to measure or to constrain neutron star equation of state models as listed here, and many complementary methods are required to reduce the systematic effects for this particular scientific goal, because systematic effects are the main problem here. So the first X-ray feature is thermonuclear X-ray burst, which provides several methods. So what is a thermonuclear X-ray burst? In a low mass X-ray binary, matter falls onto the neutron star surface, it accumulates, and at the bottom of this accumulated matter, after some time, the temperature becomes more than 10 to the power 7 degree Kelvin. So the thermonuclear ignition condition is met, and therefore intermittently this accumulated matter on the neutron star surface burns via thermonuclear runaway or unstable thermonuclear processes. And therefore, we observe in X-rays a burst like this, which lasts for a few seconds, but it is extremely energetic. Sun takes more than a week to release this energy, which is released in about 10 seconds during such a burst. And such a burst provides a few methods. First, I considered the continuum spectrum method. The burst comes from the surface of the neutron star, as I mentioned, and the burst spectra are normally well fit with a black body model, and therefore the neutron star surface area is roughly 4 pi r square, and you multiply it with sigma T observation, T obs to the power 4, T obs is measured, the total luminosity is estimated from the observed flux, and therefore we can estimate the radius of the neutron star in a very simple way. But there are many systematic uncertainties which I am not going into now because it is a very short talk. And then the next method is based on the a particular type of burst, PRE, or photospheric radius expansion burst. Such a burst is so strong that the radiative pressure pushes the photosphere or the neutron star atmosphere away from the stellar surface temporarily, And when it happens, the measured blackbody radius increases sharply and the corresponding blackbody temperature, both are observed, dips. And then as the photosphere settles down again after a few seconds onto the neutron star surface, that at the touchdown point, the temperature peaks and radius dips, and we can identify the touchdown point by such a combination of observed temperature and radius. And from this, we can estimate the Eddington flux. We assume that touchdown flux measured from here is equal to the Eddington flux, and for the Eddington flux, the radiative pressure, the force due to the radiative pressure, outward radiative pressure, is just balanced by the gravitational pull. So we know the formula of Eddington flux, which depends on mass and radius, and we have measured this touchdown flux, so we can constrain a region of this mass radius space of the neutron star. This green region is the allowed region. Another method is the Milli-Hz QPO method. As I mentioned, during a burst, the unstable thermonuclear burning happens, but burning can also happen at the border of stability and instability of thermonuclear burning. And at this border of stability and instability, we observe small frequent bursts. And they appear quasi-periodically, and therefore, if we Fourier transform the light curve or the intensity versus time profile of the source, that is X-ray intensity, then we get the power spectrum, and in the power spectrum, we see a slightly broad peak in the millihertz range because of these small bursts. And this frequency theoretically strongly depends on the surface gravity of the neutron star, which is in turn a function of neutron star mass and radius. And therefore, we can again constrain the mass radius space. The fourth method is burst oscillation method, which is a very important method. What is burst oscillation? These are millisecond period variations like this of the observed intensity during either the rise or the decay of the X-ray bursts. And what is their origin? If there is an asymmetric brightness pattern or hotspot on the surface of a spinning neutron star, then as the star spins, then the hotspot goes behind the star and comes in front of us periodically, from which we get this oscillation, which directly gives the neutron star spin frequency. And not only this, such oscillation light curves, phase-folded light curves, depends on various physical effects like Doppler boosts, special relativistic beaming, gravitational redshift, light bending, frame dragging, etc., and ultimately depends on neutron star parameters. And therefore, by modeling the shapes of these light curves, we can again measure the neutron star parameters like mass and radius, as shown here in this particular, as demonstrated in this paper in 2005. Some Bayesian technique was used to get a probability or likelihood curve of neutron star radius to mass radius. So this same method was used later, more recently in 2013, for this simulation, which was originally done for the LOFT satellite, but LOFT was not approved by European Space Agency. It is a simulation for 10 square meter X-ray instrument, and it shows that how burst oscillation can constrain the mass and radius to a very small space. And this same method is being used for the current NISA satellite and will possibly be used for future satellites like EXTP. Another method is based on accretion powered pulsation. So such pulsation happens when the accreted matter is channeled by the magnetosphere of the neutron star and forms two hotspots on the surface of the neutron stars. And again, like burst oscillation, as the star spins around its own axis, we see a periodic oscillation. This time it is much more periodic because it shows a very sharp peak in the power spectrum. Periodic oscillation in the light curve, which can again be modeled to constrain or measure the neutron star parameter in the same way, like burst oscillations. There is another method based on Kilohertz QPOs. So Kilohertz QPOs often appear in the power spectrum of some of the neutron stars, and they sometimes appear in pairs like this. This is the power spectrum of the X-ray intensity versus time profile. If we do the Fourier transform of this light curve, we get this power spectrum. And these observationally robust timing features have been detected from many neutron star low mass X-ray binaries. Although we do not know yet its actual origin, but we are sure that such a feature is originated from very close to the neutron star and hence can very well be used to measure the neutron star parameters as well as to probe the strong gravity regime. And according to almost all the models, the these uniquely high kilohertz QPO frequencies are either the following accretion disk frequencies, or the beating or resonances among them, or with the neutron star spin frequency, nu spin. And these frequencies are functions of neutron star parameters like neutron star mass and angular momentum, and therefore when we will know the actual origin of such kilohertz QPOs, which are observationally very robust features, we will be able to use this method to constrain the neutron star equation of state models. And then there is another very important method based on broad relativistic iron line. So these were originally observed from accreting black hole systems, from stellar mass black holes as well as from supermassive black holes. So they originate from the inner disk, and in the emitter's frame, this line, this is a fluorescent line, this is a narrow line, but because of various effects like the Doppler shift, because the matter is in the disk is rotating around the star, special relativistic beaming and gravitational redshift, etc., such lines get broadened, they become skewed like this, and they are shifted to the lower energies because of gravitational redshift, and finally we observe such a shifted, skewed, broad line. And they are nature-given tool to measure the black hole spin and to probe the strong gravity regime, and this observational aspect is so important because that they are basically the science drivers, one of the science drivers of some current and future X-ray satellites. So this is a very important observational feature, but up to 2006, such a line was not observed from neutron star, accreting neutron stars, but in 2007, such a line was reported from a accreting neutron star system, a low mass X-ray binary, and after that in last 10 to 12 years, such a line was observed from many neutron star low mass X-ray binaries, which has opened up a new way to measure the neutron star parameters. And this particular work detailed how to use this broad relativistic iron line to measure the neutron star parameters. This line can be used to measure the innerest radius of the accretion disk in the unit of the neutron star mass. And this quantity can be theoretically calculated by computing the structures of rapidly spinning neutron stars using the full general relativistic effect using some formalism. For example, this particular work used this Cook-Shapiro-Tucholsky formalism. And in this figure, we see that curves for various equation of state models, proposed equation of state models. So if we can measure this particular quantity, that is inner edge radius of the accretion disk from such a line with an accuracy better than 0.1, this is a number, so better than 0.1, then we will be able to constrain the equation of state models. And this could be done by the upcoming X-ray satellite EXTP, and that is why it is a primary science of the upcoming EXTP satellite, which may be launched in 2025 or so. And another method is Quiescent emission method. So I would briefly mention that many of the neutron star low mass X-ray binaries are transient sources, meaning they show big outbursts in X-rays and also in other wavelengths when their luminosity increases by several orders of magnitude for a few weeks, and then they go back to the quiescent phase, and then there is another outburst. During such a quiescent phase, in between two outbursts, the accretion rate is very small, and the most of the X-ray intensity comes from the surface of the neutron star. And therefore, like the thermonuclear burst spectrum method that I just mentioned, again, we can measure the surface temperature of the neutron star as well as estimate the luminosity from the observed flux, and therefore we can estimate the radius of the neutron star. And this should be half. And another method will be the mass measurement by the binary orbital motion, using the binary orbital motion. So in a low mass X-ray binary system, the neutron star and the companion star are rotating around each other, and therefore if we can measure the velocities, or at least the line of sight velocities of these two objects, then using Kepler's third law, we would be able to estimate the neutron star mass. And how do we measure the velocity, line of sight velocity? There are several spectral lines, for example, this Bowen complex, which is observed from the secondary companion star, or this helium line, which is observed from the accretion disk of the neutron star. These lines, as the two stars rotate around each other, they are shifted, Doppler shifted periodically with the same orbital period, like this. And from this, we can measure the line of sight velocity of the component stars, and therefore we can estimate the mass of the neutron star. Now finally, I would like to mention the current NISA satellite that was also mentioned in the previous talk. So this is the satellite which is attached to the International Space Station. This satellite can observe the neutron star low mass X-ray binaries and many of the X-ray features that I have just now mentioned, but its strength is to observe the X-ray light curves of millisecond radio pulsars. So these are non-accreting sources. These are millisecond radio pulsars in the binary systems, but there is a hotspot. There is a hotspot on the surface of the neutron star which emit X-rays, and as the star spins around its own axis, it shows the X-ray light curve with the spin period. So again, using the same technique as for burst oscillation, here this X-ray variation can be modeled and can be used to measure the neutron star parameters, particularly the radius. So this is the last slide. NISA should be able to tightly constrain the neutron star mass radius space for a few millisecond pulsars. So they claim that they would be able to measure neutron star radius with 5%, within 5% with 3 sigma accuracy. But they have not announced their results yet. For example, two of their pulsars, one is this PSR J0437, and this is another. Their mass is independently measured, so they could be especially this is the primary source for NISA. And before concluding, I would like to mention one particular aspect about equation of state models that has not been mentioned earlier. Here in this paper, a new thing has been proposed about the equation of state models. It was proposed earlier, but it has been more studied here. That several, at least two different families of neutron stars may coexist in nature. For example, there can be a family of neutron star with nucleonic equation of state model, Another family may have hybrid or quark equation of state models. And as shown here, this is the nucleonic branch, and when the neutron star becomes massive enough, for example, by accretion, or maybe it may originate as a high mass neutron star, then it can transform into a hybrid star or a quark star and jump to this branch. So there could be two branches, and therefore it would not be very straightforward by observations, even from NISAR observations, to constrain the neutron star equation of state models, because there could be two coexisting families. And with this, I would conclude. Thank you.
Thank you, Sudip. Questions for Sudip?
During the transition to the other branch, one would expect emission of neutrinos. Is there an estimate of what kind of luminosities in neutrinos are expected when there is a transition?
It is not formally expected, but it will be similar to the the neutrino that is expected for supernova, that is when the neutron star is born. So about 10% of the rest mass roughly would be converted into energy, and most part of it will be in the form of neutrino.
Any other question?
So maybe I missed it. What are these hot spots on the neutron star surface due to?
Which slide?
The hot spots which emit X-ray and which can give you a very good constant assessment.
Yes, so
origin I'm just asking.
there can be many reasons. For example, burst oscillations. Yes. So radio pulsar is a different thing, and radio pulsar is a strong magnetic field, and this matter is emitting. Are you asking anything?
No, I'm just asking about those hot spots on the neutron star surface. Basically, they can directly give you, neutron star spin frequency plus other things also. Yeah, I'm just asking this.
Yes. So your question is, why this hotspot is there?
Yeah.
So, for example, here this is the burst oscillation. So thermonuclear burst can be ignited at a particular point on the neutron star surface, right? And a hotspot is created. So during the rise of the burst, this thermonuclear flame spreads all over the neutron star for a short amount of time, maybe for 1 second. This will be an expanding hotspot on the neutron star surface. So this is one origin of hotspot. Another thing is this, as I showed here. For an accretion-powered pulsar, accreted matter is channeled onto the polar cap, magnetic polar cap on the neutron star. And then most of the emission is coming from there. So that is another reason of hotspot. So for different reasons, hotspot can be created.
Okay, Satya, last question on this talk, and then we'll open the floor for the full session.
So you mentioned many different methods for measuring the equation of state and also radius.
Yes.
When do you think we will have at least something like 3 or 4 such measurements available, so that we have we can build a consistent picture or understand systematics in different methods?
So the reason I have not showed any results, that the constraints, I have shown only the methods and simulations, because it's not because that there are not any results. There are some results published for over the years, but I believe those are heavily affected by various systematics. So there is no point to show results at the moment, but our best hope currently is NISAR, which will, using the non-accreting neutron star, they will possibly constrain in a good way. And in future, EXTP or some other satellites with some bigger area, they will possibly be able to observe several such observational features, and then we will be able to combine them, and we'll have a very strong constraint on some of the neutron
The
stars.
reason I'm asking is the time scale is important to understand, because is this a problem that requires a decade to solve, 2 decades, or 2 years?
So all I say that from electromagnetic signal, neither is the best hope, and neither can
Just one result, one neutron star.
this for they have four at least, but one is their best in
That's
pulsar.
right. That's what I meant. Yeah.
But there are others. So for that pulsar, for at least couple of pulsars, the mass is independently measured. So they can assume that mass, and they can only measure radius. So I think that they will be able to constrain quite well, as they have claimed that 5% with 5% error with 3 sigma confidence. So that much we can expect.
I have heard that systematics is still not completely controlled, right? Even in that case, there's a lot of modeling that goes in.
That is true. Systematics are there. While we want to solve this problem, we want to measure the neutron star parameters or to constrain equation of state models, we have to look at it through a very complex filter of astrophysical phenomena.
That's right. Yeah. So the satellites that you mentioned, is it the time scale is what?
It is up there. They should have published by now, but any time it can happen.
The data has already been acquired, and they have been analyzing it. One hypothetical scenario is that they actually give you 2 radius measurements using 2 different models, primarily for that. And there could be a systematic there, although the precision still might be about 5%. Yeah.
We don't know when they.
Yeah. We'll have to see. Yeah, that's hypothetical. So okay, now the floor is open for the full panel. But Alexander, did you have a? Okay, Pratim.
So I have a naive question. So when you in the burst you see the scattering tail, and from the scattering tail, I'm guessing you can say something about the environment around the neutron star, right? When in the burst you see a scattering tail, right?
Scattering tail. Where is the?
You have a.
You mean the tail of the burst?
Yeah. So which goes as like lambda 4.
It's not scattering tail. It's cooling down. The surface of neutron star is cooling down. So you mean this one?
Yeah.
So it is burning, and the thermonuclear flame spreading, and then the entire surface has been burnt, the entire matter, accumulated matter, and then the surface slowly cools down here. That is the tail.
This kind of a profile which you're getting, is it something which goes like lambda to the power 4 or something like that, right? Is it true or?
These varies from burst to burst. It is roughly exponential type, but it varies from burst to burst.
So can you say something from the, so it's more like if you have a glitch and you see how it is falling down, can you say something about the properties of the neutron star from how it is falling down?
So what do you mean by glitch?
I'm just comparing, if you have a glitch in a neutron star, or a pulsar, and depending on how it falls down, you can say something about the.
Of course, this is entirely different from the glitch. That is entirely different physics and origin. Here, only the surface, which there was burning on the surface like a forest fire, and now everything is burnt up and it is cooling down. And yes, how it is cooling down, that could say something about the neutron star atmosphere. And also it could say something about what are the chemical elements that are burning there. Because for different types of chemical elements, this cooling tail could be longer in time or shorter in time, or there could be, people have also proposed in the thermonuclear burning, it's a complex burning, for example, it could be CNO cycle or rapid proton capture process. So there could be some waiting points where it can cool a little bit and then heats up again. So there can be a lot of things people have proposed that could be understood from such a tail if such a burst is observed with a future much bigger instrument.
So if you, now it's a broader question, if you get to know about it, is it possible to use that in the templates that we build, the longer run?
Okay, let me channel that into, so bringing in gravitational waves, right? So one can imagine a few different ways of integrating these observations with gravitational wave observations. One is that you obtain posteriors for different systems, because that's more likely, in, for example, the mass radius plane, and see, which clutch of equation of state curves perhaps satisfy both of those posterior constraints. That could be one. But there are others, for example, for the quiescent emission method, right, where there are superbursts, but maybe during those episodes, there is an induced ellipticity that is large enough to emit gravitational waves. But because we know the spin frequency from electromagnetic observation, and of course the location, it improves our confidence in these measurements, right? Because again, the Charles factor is less for this continuous wave, gravitational wave sources.
That is true. So these are the systems which can ultimately generate continuous wave, continuous gravitational waves. So we can kind of combine any information from continuous gravitational waves with the information that is provided here. We can still combine such information with the information we get from merger, although these are not merging sources, these are two different types of sources. But at the level of nuclear physics, suppose some nuclear physics parameter we constrain from here and from merger, and then we can combine them and we can try to get a better constraint at the level of nuclear physics. That is also possible.
Sanjeev?
Okay, so this is to Bandyopadhyay. Yeah, so you talked about this phase transition in the thing. So what is the time scale for this change in equation of state, or?
Time scales for phase transitions.
For that.
Oh, these are static calculations. These are not dynamical calculations. So definitely we did not calculate time scales here. Yeah.
I thought they were like tenths of microseconds or something like that. Somewhere.
No, I am not aware of it. Yeah, surely not. But I posed one question, that is, what will happen to this lambda 1, lambda 2 plot in a binary merger event involving two solar mass neutron star?
So you're okay. So the speaker is posing a question. Yeah, that's perfectly allowed. So to understand, you're talking about two solar mass components in a binary. Is that okay? One of them is 2. Another one could be anywhere between 1 and 2. These merge. Oh, and so from the gravitational waveform of such a binary, what can we tell about lambda 1 and lambda 2? Maybe I should allow another speaker to answer that, Wolfgang?
I'm not sure I understood the question. Could you repeat that?
How would the lambda 1, lambda 2, posteriors change if, let's say, it's the same GW170817 with one difference, namely that the higher mass object has is actually 2 solar mass object?
Okay. I don't know. But I have a follow-up comment on how to compare basically results.
I mean, the one obvious difference will be that the lambda value will be smaller for the heavier object. So the posterior will, of course, is expected to shift if everything about the data analysis is correct.
Well, it would certainly be different. Probably the other tidal deformability would be then more strictly constrained because you don't have the generation anymore between parameters. But what exactly comes out, one just would have to try.
But are you ultimately getting after some nuclear physics parameter from these measures?
We have ruled out some stiff equation of state depending on this GW170817. So whether this kind of new event involving a 2 solar mass neutron star in the binary merger, those equation of state will be again favored or not.
There are, as we saw, there are systematics involved from the choice of the waveform models, as Wolfgang said, but also exactly the type of system we are seeing in a particular stretch of noisy time series data may also have some imprints. We know that already because even for the binary black hole, post-Newtonian coefficient tests, Although they're all consistent with 0, but there is actually a shift in one direction more than the other. But it is true that if you observe more disparate systems, then as has been shown by Chris and several others, especially if you have many systems with very different masses, then it is we are able to sample for example, the mass radius plane more comprehensively and pin down the equation of state better. That is one reason where population synthesis models will have important implications, and there is a separate session on that. The masses of neutron stars may not be distributed uniformly. I mean, the galactic ones are not. But if they were, some of us may say that the equation of state parameters will get constrained better because, again, we are able to sample the mass space more. Yes, Volkan.
So, yeah, a follow-up comment on how to best combine different observations. And I think that is an important strategy question. So I would opt to stay as close to the data as possible. So, for example, if I compare equation of state models to a gravitational wave observation, I would not use the radii, but I would use the effective tidal deformability posteriors. Because if, for example, I get the radii that were computed using some universal relation with purely hadronic equation of state as calibration, and then I compare that to some exotic quark star model, what does it even tell me? I mean, then I have to disentangle again what was the model dependence on the mass radius inference in the gravitational wave results. So it's much cleaner and makes life much easier to just stay close to the data. And I think that is also what's done in the isolated pulsar observations. They always compare the stuff that can actually be observed, right? And put that as a line in whatever space you're working in.
The interior magnetic pressure also supports it also contributes in supporting the mass of the neutron star. So without knowing the nature of that interior magnetic field, how will the mass radius could constrain the equation of state?
The magnetic field inside the star has some effect on the radius of the star. So without knowing the details of the magnetic field, how can we conclusively infer the radius and therefore make comments on the equation of state? Go ahead.
I mean, there have been studies in the past how strong a field you would need to actually have a significant deformation. And people have gone up to absurd field strengths where you wouldn't even have atoms anymore in the atmosphere, but just spindles of electron orbits. But for realistic field strengths, let's say magnetar level, this effect is much smaller than all the other errors we already have from other effects.
Okay, so yeah, I can imagine there are still some unanswered questions, but that's why we are breaking for lunch. The speakers are going to be around. I too have some questions to ask them. Feel free to talk to them at lunch. Thank you.
So thank you, Sukant, and all the panelists. So we'll come back by 2. So please try to make it.